It's time to start drawing molecules with this Lewis dot structure, where the dots represent the valence electrons. And by drawing these valence electron dots, we should be able to predict the covalent bonding between these atoms. Let's look at some easy molecules first. For example, how about number 6? Let's jump to number 6. I2. So 2 atoms of iodine. Iodine is a halogen, and all halogens have 7 valence electrons. Sounds easy enough. So I'll draw my iodine, iodine. Around each iodine are 7 valence electrons. They're organized as 6 paired electrons and 1 single. There's my 6 paired electrons and 1 single. Same thing with the other iodine. Now, after a while, you'll get good at predicting the bond. Obviously, the bond is going to occur between the 2 iodine atoms. They're going to share electrons in order to get a full octet. Well, you can kind of tell, like, here's my oddball. I'm probably going to want to share or bond that oddball electron so that I can get 8. So with the other iodine, we'll draw our dots, our 7 valence electrons, but we'll draw them almost like a mirror image because I want the 2 single electrons facing each other. I want the single electrons facing each other because that's where the bond occurs. In the center here, they're going to share this electron pair. And by sharing that pair of electrons, it counts for both iodine atoms, and they both get an octet. 2, 4, 6, and then 7, 8. 2, 4, 6, 7, 8. The pair in the middle counts for both iodine. Perfect. Everybody gets an octet. There's covalent bonding. We try to match up the single dots because those are the electrons that we want to share. The other electrons are paired in their orbital, and that's stable. Now, there's a couple different ways you can show the bond. This is one option. You can circle the single dots to show that the pair is shared between the 2 atoms. Or let's say I do it like number 2. Here's another quick, easy one. Hydrogen and fluorine. Hydrogen only has 1 valence electron, so we'll give him 1 dot. Fluorine has 7. And again, I want the single electrons to match up, so you can kind of rig it after a while. Like, you'll figure this out. Well, I'm going to put the single dot toward the center because I want there to be a bond between the hydrogen and fluorine atoms. And then we'll give the pairs to the outside. 7 valence electrons on fluorine. So one option, you could circle the shared pair like in number 6. Or more often, to be honest with you, I just connect the dots. I just connect the dots and I link them up like that. And whenever I see a dash between 2 atoms, it's understood that it's a pair of 2 electrons being shared between the 2 atoms. Whichever you're more comfortable with is totally fine with me. Circle them, connect the dots, either is A-OK. Now these things always work out. These drawings always work. The dots always match up. Try something like 4. Carbon and 4 hydrogen. Now they give me a couple little hints up on top. Hydrogen and halogens like to go on the outside of the molecule. Well, think about it. Hydrogen only has 1 valence electron, and he's actually only going for 2. Sometimes we call hydrogen a deficient octet. It's an atom that's stable with less than 8. So like in this molecule number 2, this shared pair counts for hydrogen and fluorine, but then hydrogen only has 2, and that's okay. He's just filling the first energy level, and it can only hold 2 electrons. Which means then that hydrogen only wants to make 1 bond. He already has 1 electron. He only needs 2. Kind of the same thing with halogens. They only want to make 1 bond. They have 7 valence electrons. They want 8. They'll only make 1 bond. So hydrogen and halogens will usually go toward the outside of your molecule. If you only have 1 atom of a particular element, that's probably the atom that goes in the middle. For example, carbon, CH4, we only have 1 carbon, so we're probably putting the carbon in the center. Which it also tells me up on top, hint number 3, is that carbon will always be in the center. Carbon with his 4 valence electrons. And we could add that too, as kind of a hint. The atom in the middle is always the atom that makes the most bonds. Carbon makes 4 bonds. That's a lot. That's the most of all the molecules that we'll look at. So carbon will always go in the center. Carbon has 4 valence electrons. He wants 8, meaning that carbon wants to make 4 bonds. Perfect. We have 4 hydrogen. And again, you kind of figure this out the more molecules you draw. I want the bonds to occur with the single electrons. So I'll purposely match up the single electron with hydrogen to the single electron of carbon. And then I know I can either link them up or connect the dots, circle them. There's my single bond. A single covalent bond is the sharing of 2 electrons. And then we just go around the outside and we add all 4 hydrogens. And so again, I'll put this dot on the bottom of hydrogen because I want it to line up with the single dot of carbon. And then here we'll put the dot on the top of hydrogen so that all the single dots match up. We can connect them, we can circle them. Here we go. CH4 done. The hydrogens have their duet. Sometimes we call it the duet rule with hydrogen. They only need 2 valence electrons. He's just filling the first energy level. And the carbon has an octet. All of these pairs count for both atoms. 2, 4, 6, 8 electrons on the carbon. Done. Oh, this isn't so bad. And now again, if we skip around a little bit, let's check number 5. Number 5 has more carbon. You've got carbon, hydrogen, and 3 chlorine. So there's only 1 atom of carbon and 1 atom of hydrogen. But carbon's got to go in the middle. Between carbon and hydrogen, carbon can make 4 bonds. 2, 3, 4. Hydrogen can only make 1 bond, so you'll always be on the outside. So you can put the hydrogen anywhere. It doesn't matter on which of these 4 positions. I don't know, maybe I'll throw them on the top. Done. Then perfect. My carbon has 1 bond, but needs 3 more. And you've got 3 chlorine. So we'll hook on the chlorine. Halogen, 7 valence electrons. And we'll purposely line up the single electron so that we can connect them in a single bond. The sharing of 2 electrons. Then we'll go around the outside and hook on the other chlorine. Single, 2, 3, 4, 5, 6, 7. And another chlorine. I'll put the singles together. 2, 3, 4, 5, 6, 7 valence electrons. Connect the dots. 1, 2. Everybody's got an octet. Except for hydrogen, and he's okay with a deficient octet. Hydrogen has his 2 valence electrons. Carbon has 8. The chlorines also have 8. Now sometimes you might see a question on a test that would say, how many bonding electrons are around the chlorine? Each chlorine atom has 2 bonding electrons and 6 non-bonding electrons. Or sometimes we call these lone pairs, lone electron pairs, or maybe they're called non-bonding electrons. They're very important because we have to prove that chlorine has an octet. But not all of the electrons have to be in bonds. Chlorine already had 6 paired electrons, and now by sharing one with carbon, we can pair his 7th electron. Now we have an octet, 8 valence electrons. But you have to draw those dots around the chlorine. Sometimes people get kind of lazy, but the dots represent the octet around the chlorine. Cool. So then the last one's water, H2O. 2 hydrogen, 1 oxygen. Hydrogen always wants to go on the end, so we're probably going to start with the oxygen. Oxygen has 6 valence electrons, and they're organized as 2 pairs and 2 singles. And now again, you can be a little bit creative. It doesn't matter where you put the pairs and where you put the singles, as long as they're organized as 2 pairs and 2 singles. Because the single electrons are where the bonds go. And so again, oxygen wants to make 2 bonds. He already has 6 valence electrons, wants 8. So I can totally see where to put the hydrogens. The hydrogens will purposely go next to the single electrons of oxygen. We'll line up the single dots, the single electrons, so we can connect them and make single bonds. Everyone has an octet. The hydrogens each have 2, which is fine, they're duet. And again, the oxygen, if they ever say, how many bonding electrons are around the oxygen? 4. The oxygen atom has 4 bonding electrons and 4 non-bonding electrons. Or sometimes they might say 2 bonding pairs of electrons and 2 non-bonding pairs. Which again, those non-bonding pairs are very important. You have to put those extra dots on the oxygen to prove that he has a full octet. And the last one, nitrogen, is probably going in the middle. I only have 1 atom of nitrogen, and he has 5 valence electrons, organized as 1 pair and 3 singles. And so again, can you kind of see that if you put those dots correctly around the central atom, the bond just jumps off the page? Oh, yeah, I can totally tell. Nitrogen wants to make 3 bonds. We're going to bond by those 3 single electrons, and perfect, I have 3 hydrogen. So hook on the 3 hydrogen. 1, 2, 3. We'll line up those single electrons and share in a single covalent bond. And again, we all have octets except for hydrogen. Nitrogen has 1 set of non-bonding electrons, 1 pair of non-bonding electrons. And then we have 3 pairs of bonding electrons. We do have an octet on the nitrogen. And now again, technically, you can put that pair anywhere. You can put the pair on the side, on the bottom, that doesn't matter. You have to picture in your mind that these are 3-dimensional structures. So I could take this molecule and like flip it or turn it in real life, and then it would look like the double bond is on the side. Or I could flip it upside down and it would look like the double bond is on the bottom. On paper, we're trying to draw a 3-dimensional structure. It doesn't matter where you put that lone pair on paper, as long as you have it to prove nitrogen has an octet. So there's a few other ones which I think I would suggest. Give these a try, 7, 8, 9, and 10. Maybe pause the video at this point, try these guys, and then bring it back to see if you drew them right. Here are the answers then to the last few. Now after a while, I think you'll start noticing some patterns and trends. I can't do a whole lot on a test or quiz to make this very difficult for you. Any atom in the oxygen family will have the same electron dot structure or Lewis dot structure. If they all have 6 valence electrons, they'll all have their electrons organized in the exact same way. 2 pairs and 2 singles. So maybe this one is in the homework or in the practice study guide here. Sulfur and 2 chlorine. Maybe on a quiz I give you oxygen and 2 chlorine. Well, oxygen is in the same family as sulfur, so the electrons look exactly the same. You just switch the sulfur to an oxygen, same structure. Or I could get really crazy, and maybe I switch the sulfur to an oxygen, and I switch the chlorine to a different halogen. Switch it to bromine. Can you see that it's the same structure? As long as I pick elements that are in the same family, their electron dot structure will look exactly the same. And now again, you can put these pairs and singles in a different arrangement around the central atom. So you could have gone, like sulfur. Maybe you did something like this. That's okay. Maybe you did sulfur and you put the pairs on the top and bottom and the singles on the side. That's okay. Again, we're trying to draw something that's 3-dimensional, and eventually we'll get out the model kits and we'll build these molecules so that you can twist and turn them in real life. On paper, it doesn't matter how you arrange your dots and your you should say your paired dots and your single dots. Number 8, arsenic is in the nitrogen family with 5 valence electrons. So again, if I give you any element from the nitrogen family, it's going to look exactly the same. They all have 5 valence electrons organized as a pair and 3 singles. So I could switch the central atom to nitrogen, and it's the exact same structure. I could switch it to phosphorus. It would look exactly the same. I could switch the fluorine to any other halogen. I could switch it to chlorine, bromine, iodine, and it's the exact same structure. So again, if I'm picking elements from the same family, the Lewis dot structure will look exactly the same. There's not a whole lot I can do on a test or quiz to try to trick you. Number 9, carbon. Carbon likes to make 4 bonds. So you'll always find things to hook on to those 4 single electrons on your carbon. Previously, we drew carbon with 4 hydrogens. We drew carbon with a hydrogen and 3 chlorine. Here's 2 hydrogen and 2 fluorine. No matter what, there will be enough things to hook on your carbon to fill those 4 valence electrons and give carbon an octet. And now again, it doesn't matter where you draw the fluorine and the hydrogen. On paper, you could go hydrogen, hydrogen, fluorine. You could put the fluorine on the bottom, and you could put the fluorine on the side. That wouldn't matter. As long as you have the 2 fluorine and the 2 hydrogen, your hydrogen has 2 valence electrons, your fluorine has an octet with 8, and your carbon has an octet. It doesn't matter where you put the 2 hydrogen and the 2 fluorine. Which is kind of the same gig as number 10. There's a lot going on. Your central atom will be the silicon, which is in the carbon family, 4 valence electrons. You've got 2 hydrogen. You can put those hydrogen anywhere. And then you have 2 OH groups, which you might recognize as hydroxide. In the hydroxide group, people were asking this a while ago when we did polyatomic ions. They said, why is it hydroxide, like hydroxide, but oxygen comes first in the Lewis structure? Because that's how it hooks on to the molecule. Oxygen wants to make 2 bonds. The oxygen has 2 single electrons. No matter where you draw them, there are two single electrons. Hydrogen only wants to make one bond, so the hydrogen is always on the end. And now again, you can be a little creative. You can put the two hydrogens and the two hydroxide groups anywhere around the central silicone. And again, depending on how you draw the dots on your oxygen, maybe you drew the singles, one here, one there. Maybe you drew your singles, one here, one over there. It doesn't matter. As long as you had two singles and two pairs on your oxygen, you're proving that oxygen will have an octet. 4 non-bonding electrons and 4 bonding electrons. So you can be a little creative in how you link things together or where you arrange them around your central atom, as long as you prove that everyone has an octet except for hydrogen. He only needs 2. And I think you'll start finding as you draw more and more structures that there's not a lot I can do to make this any more difficult for you. If I pick any element in the same family, they'll all have the same electron structure, which means they all form very similar bonds.